In this video, we'll talk about how to fit the parameters theta for logistic regression. In particular, I'd like to define the optimization objective, or the cost function that we'll use to fit the parameters. Here's the supervised learning problem of fitting a logistic regression model. We have a training set of m training examples, and as usual, each of our examples is represented via a feature vector that's n plus 1 dimensional. And as usual, we have x0 equals 1, first feature, or 0 feature is always equal to 1. And because this is a classification problem, our training set has the property that every label y is either 0 or 1. This is our hypothesis, and the parameters of the hypothesis is this theta over here. And the question I want to talk about is, given this training set, how do we choose or how do we fit the parameters theta? Back when we were developing the linear regression model, we used the following cost function. I've written this slightly differently, where instead of 1 over 2m, I've taken the 1/2 and put it inside the summation instead. Now, I want to use an alternative way of writing out this cost function, which is that instead of writing out the squared error term here, let's write in here cost of h of x, comma y, and I'm going to define that term, cost of h of x, comma y, to be equal to this. It's just equal to this 1/2 of the squared error. So now we can see more clearly that the cost function is a sum over my training set, or is 1 over m times the sum over my training set of this cost term here. And to simplify this equation a little bit more, it's going to be convenient to get rid of those superscripts. So just define cost of h of x, comma y to be equal to 1/2 of this squared error. And the interpretation of this cost function is that this is the cost I want my learning algorithm to have to pay if it outputs that value, if its prediction is h of x and the actual label was y. So let's just cross off those superscripts, right? And no surprise, for linear regression, the cost we've defined is that, well, the cost for this is that is 1/2 times the square difference between what it predicted and the actual value that we observe for y. Now, this cost function worked fine for linear regression, but here we're interested in logistic regression. If we could minimize this cost function that is plugged into J here, that would work okay. But it turns out that if we use this particular cost function, this would be a non-convex function of the parameters theta. Here's what I mean by non-convex. We have some cost function j of theta, and for logistic regression, this function h here has a nonlinearity, right? It says 1 over 1 plus e to the negative theta transpose x. So this is a pretty complicated nonlinear function. And if you take this sigmoid function, plug it in here, and then take this cost function and plug it in there, and then plot what j of theta looks like, you find that j of theta can look like a function that's like this, with many local optima. And the formal term for this is that this is a non-convex function. And you can kind of tell, if you were to run gradient descent on this sort of function, it is not guaranteed to converge to the global minimum. Whereas in contrast, what we would like is to have a cost function j of theta that is convex, that is a single bow-shaped function that looks like this, so that if you run gradient descent, we would be guaranteed that gradient descent would converge to the global minimum. And the problem with using the squared cost function is that because of this very nonlinear sigmoid function that appears in the middle here, j of theta ends up being a non-convex function if you were to define it as the squared cost function. So what we'd like to do is to instead come up with a different cost function that is convex, and so that we can apply a great algorithm like gradient descent and be guaranteed to find the global minimum. Here's the cost function that we're going to use for logistic regression. We're going to say that the cost or the penalty that the algorithm pays if it outputs the value h of x, so if this is some number like 0.7, right? But if it predicts the value h of x and the actual cost label turns out to be y, the cost is going to be minus log h of x if y is equal to 1, and minus log 1 minus h of x if y is equal to 0. This looks like a pretty complicated function, but let's plot this function to gain some intuition about what it's doing. Let's start off with the case of y equals 1. If y is equal to 1, then the cost function is minus log h of x. And if we plot that, so let's say that the horizontal axis is h of x, so we know that our hypothesis is going to output a value between 0 and 1. Right? So h of x varies between 0 and 1. If you plot what this cost function looks like, you find that it looks like this. One way to see why the plot looks like this is because if you were to plot log z with z on the horizontal axis, then that looks like that, and it sort of approaches minus infinity, right? So this is what the log function looks like. And this is 0, this is 1. Here, z is, of course, playing the role of h of x. And so minus log z will look like this, right? Just flipping the sign, minus log z. And we're interested only in the range of when this function goes between 0 and 1. So get rid of that. And so we're just left with, this part of the curve. And that's what this curve on the left looks like. Now, this cost function has a few interesting and desirable properties. First, you notice that if y is equal to 1 and h of x is equal to 1, in other words, if the hypothesis exactly predicts h equals 1 and y is exactly equal to what it predicted, then the cost is equal to 0, right? That corresponds to the curve doesn't actually flatten out. The curve is still going. First, notice that if h of x equals 1, if the hypothesis predicts that y is equal to 1, and if indeed y is equal to 1, then the cost is equal to 0. That corresponds to this point down here, right? If h of x is equal to 1, and we're only considering the case that y equals 1 here, but if h of x is equal to 1, then the cost is down here, is equal to 0. And that's what we'd like it to be, because if we correctly predict the output y, then the cost is 0. But now notice also that as h of x approaches 0, so as the output of a hypothesis approaches 0, the cost blows up and it goes to infinity. And what this does is this captures the intuition that if a hypothesis outputs 0, that's like saying our hypothesis saying the chance of y equals 1 is equal to 0. It's kind of like going to a medical patient and saying the probability that you have a malignant tumor, the probability that y equals 1, is 0. So it's like absolutely impossible that your tumor is malignant. But if it turns out that the patient's tumor actually is malignant, so if y is equal to 1, even after we told them that the probability of it happening is 0, so it's absolutely impossible for it to be malignant. But if we told them this with that level of certainty and we turn out to be wrong, then we penalize the learning algorithm by a very, very large cost. And that's captured by having this cost go to infinity if y equals 1 and h of x approaches 0. This slide considered the case of y equals 1. Let's look at what the cost function looks like for y equals 0. If y is equal to 0, then the cost looks like this. It looks like this expression over here. And if you plot the function minus log 1 minus z, what you get is the cost function actually looks like this. So it goes from 0 to 1, kind of like that. And so if you plot the cost function for the case of y equals 0, you find that it looks like this. And what this curve does is it now blows up and goes to plus infinity as h of x goes to 1, because it's saying that if y turns out to be equal to 0, but we predicted that y is equal to 1 with almost certainty, with probably 1, then we end up paying a very large cost. Let's plot the cost function for the case of y equals 0. So if y equals 0, that's going to be our cost function. If you look at this expression, and if you plot minus log 1 minus z, if you figure out what that looks like, you get a figure that looks like this, which goes from 0 to 1 with the z-axis on the horizontal axis. So if you take this cost function and plot it for the case of y equals 0, what you get is that the cost function looks like this. And what this cost function does is that it blows up, or it goes to a positive infinity as h of x goes to 1. And this captures the intuition that if a hypothesis predicted that h of x is equal to 1 with certainty, with like probably 1, it's absolutely got to be y equals 1. But if y turned out to be equal to 0, then it makes sense to make the hypothesis or make the learning algorithm pay a very large cost. And conversely, if h of x is equal to 0 and y equals 0, then the hypothesis nailed it. It predicted y is equal to 0, and it turns out y is equal to 0. So at this point, the cost function is going to be 0. In this video, we've defined the cost function for a single training example. The topic of convexity analysis is beyond the scope of this course, but it is possible to show that with our particular choice of cost function, this would give us a convex optimization problem. As our cost function, our overall cost function j of theta will be convex and local optima free. In the next video, we're going to take these ideas of the cost function for a single training example and develop that further and define the cost function for the entire training set. And we'll also figure out a simpler way to write it than we have been using so far. And based on that, we'll work out gradient descent, and that will give us our logistic regression algorithm.